Now we discuss about the gradient of a multivariable function. So given a function of two or three variables, we can create a vector valued function from that scalar valued function. Okay. So here the function f is from the say R2 or R3 to R. For example, I consider f of xy equal to say x square minus 3xy square. Then using the first order partial derivatives of f with respect to the variables, that is dou f by dou x, which is equal to 2x minus 3y square, right? And dou f by dou y, which is minus 6xy. So using these two partial derivatives, we can create a vector valued function which will be denoted as del f, and del f at x comma y is defined as the partial derivative of f with respect to x I plus partial derivative of f with respect to y j. Or this can also be treated as a point like dou f by dou x comma dou f by dou y. Okay. At any point x comma y, del f will give you a vector corresponding to that. For example, if you consider del f at 1 comma 0, this is going to be dou f by dou x at 1 comma 0 is 2 minus 3 into 1 square, so 2i, and dou f by dou y at 1 comma 0 is 0, so 2i plus 0j. Or you can correspondingly you can take the point as 2 comma 0. You can use del f as a vector. Okay, so this function is called the gradient of a scalar valued function which is of more than one variable. If there is only one variable, you will not get a vector valued function. But if you have more than one variable, then you can create so-called the gradient of a function of two variables of f of xy. You can say f of x comma y comma z also you can treat. Why? Because if there is one more variable z, then dou f by dou x, dou f by dou y, and dou f by dou z will be there, and you can create the corresponding vector valued function grad f. This is read as grad f. So formally, if f is a function of x and y, which is having partial derivatives fx and fy, then the gradient of f is defined as del f of xy is equal to fx of xy times I plus fy of xy times j. If f is a function of three variables, similarly you can define. Okay, and one of the important uses in calculating the directional derivative. And before going to that, let us see the properties of gradient. Since gradient is nothing but partial derivatives, and partial derivatives satisfy all the laws of differentiation, you can see that del of kf, where k is a constant, is equal to k into del f. Del of f plus g or del of f minus g will be del f plus del g or del f minus del g. And del will satisfy the product rule also, that is del of fg is equal to f into del of g plus g into del of f. And quotient rule also is valid for g not equal to 0, that is del of f by g is equal to g into del f minus f into del g divided by g square. So these are some of the important properties of gradient. You should always keep in mind that gradient is defined only for a scalar valued function. That is a function which is of more than one variable, but its image should be scalar value, scalars. That is scalar valued function or real valued function. So for such a function, you can define the gradient, and gradient is always a vector valued function. And this will be of immense use in vector calculus, like when we study divergence, curl, etc. And also it is of help in calculating the directional derivative as well as the tangent vector, normal vector, etc.